chosen three different types of composite materials here. This is aimed primarily for my engineering studies students sitting for the high school certificate, and we've covered ceramics and we've covered corrosion. Now we're looking at composite materials. A composite is a structure made up of more than one distinct material. They can be roughly categorized in three different ways. You can look at them as particulate. So this is a disc brace pad, and you can see that the surface over here is made up of a number of different materials. There's some resin binding it together and various different metals, some cast iron or brass. And they're little particles, so they're round sort of particles. So this would be a particulate composite. The other thing that some composites can be is laminar. So here's a bit of plywood, and we'll talk more about this later on, but you can see there's sort of laminations where sheets of plywood are put together face to face, not edge to edge, to provide strength properties which the original timber doesn't have. And they can also be fibrous, and this is a little bit of fiberglass over here. It has a resin matrix, or a resin soup if you like, and glass fibres are embedded into that soup and changing the properties of the material, so it's quite stiff and hard, and you can see the fibres there. So three different types: particulate, like that, small round particles. They can be laminar, like the plywood, or they can be fibrous, a fibre composite, like the fiberglass that I'm holding here. Now, while we're about this, composite material is usually made up of two different sections. They're made up of a matrix, which serves to hold parts together, and reinforcements, which provide desired surface properties of the composite material. The reinforcements are held together and used by the matrix, and the matrix allows a transfer of force to go from outside the object onto the filler portions. So essentially it holds it all together. The matrix, it provides bulk, it can provide some heat resistance or thermal stability properties if those are desired, and then it allows force to be transferred onto the main load bearing structure, which is the filler. Okay, so there's three different types. Now the syllabus requires us to talk a little bit about timber, concrete, asphalt, laminates like such, like the plywood, and geotextiles. Unfortunately, I don't have a geotextile to show you, but I'll try and show you examples of everything else. Okay, so we've spoken about a matrix and a reinforcement, or a filler, and another good example of that would be a carbon fibre. And carbon fibre is an example of some carbon fibre. This is a chain guard of my motorbike, and it's carbon fibre, and you might be able to see, if I hold it up to the light like that, you can see underneath the resin, the shiny resin, a woven fabric, and that fabric is carbon fibre. Quite expensive and quite light and strong, high tensile strength, very high strength to weight ratio. Quite expensive because of its manufacturing process. It's a long, extended and energy rich manufacturing process, which really ups the price of the carbon fibre. And you look on the other side, you can sort of see it doesn't have the glossy finish, but you can start to see the fibre appearing there. It's very tightly woven fibre. So that's an example of a matrix, and the strength of the matrix, or the product, coming from the carbon fibre, and the matrix holding it all together and providing some filler material, and in this case a surface finish, and transferring the force onto the carbon fibre. Okay. Plenty of other examples of that. The reinforced concrete, which we'll talk about in just a minute. Okay, now from ancient times there's been use of composites, and a classic use of a composite would be, if you read the Bible, where Pharaoh got Moses and his people to make bricks without straw. So there was a brick shaped in a mould, and the mould would have been like so, and the brick came out of that mould, and inside the brick were tiny fibres of straw, helping to bind the mixture together. Remember, they weren't fired, they were just sun-dried clay bricks in that particular case. So the bricks held together by the straw being the reinforcement, and the clay of the brick being the matrix. Alright, other examples of ancient uses of composite structures would be an ancient bow, so especially if you look at the recurve bow, which would look a little bit like this when it's strung like that. Oftentimes the handle area over here needed to be very stiff and very hard, whereas the sections of the arm of the bow needed to be flexible and very resilient, able to store lots of strain energy. So the bow here would often be made of, or this hand section would be made of animal bone, like for example a buffalo horn, and the bow itself over here would be made of several different types of wood, laminated together, just like you see here in the plywood, and glued. So it would be glued laminates of wood, and that would provide a very tough, resilient, and powerful weapon to be able to be used in war. So another ancient use, and these have been used for thousands of years. Okay. Now, additional uses of ancient materials were pozzolana concrete. Now we look at concrete. Here's an example of some concrete. This is Portland cement, or Portland-based concrete rather than pozzolana. The pozzolana relied on some crushed up volcanic rock, and it had a similar kind of process as using lime and other materials to be able to create a concrete. Now, Portland cement, the same sort of process. We have a cement, which is the matrix, and binding together particles of sand and of volcanic rock, igneous rock, like basalt, or I guess the common name is blue metal that's used, but it's really just a stone, not a metal. Very tough, hard-wearing stone. So the properties of the stone are desired. The hard-wearing toughness of the stone is what's required, and the sand also, the hardness of the sand, and the cement provides the means by which the force can be transferred to those, holds them all together in position for use, and we get a hard-wearing, tough, easily able to be shaped material, composite material, which is concrete, whether pozzolana or Portland concrete. Okay, some more historical use. Now, it's probably very good at this point in time to talk about concrete, seeing as we're discussing it, and have a look at modern uses of concrete. And this is a little model of a beam, and you may be able to see inside the beam here. It is a composite structure because it has more than one phase. And in this case, you have metal placed inside there, the reinforcing metal over there, and we have some concrete set around those metal reinforcing bars. Now this beam is quite different from this other one which I showed you a sample of earlier, which was unreinforced. When I put some force on the unreinforced beam here, it cracked very easily, almost immediately, and suddenly. I had to put much more force on this beam over here, and when it failed, it only failed slightly. There was some cracking at the bottom, force coming at the top, so therefore the bottom was in tension and it began to crack, but very slowly the crack started to travel and there was deformation before, and in fact it never even really fractured, it just bent, plastically deformed. So what that says to us is that the properties of concrete, which are hardness and brittleness, have been considerably modified by placing it or mixing it with steel, in this case mild steel, galvanized mild steel wire. But in real life, instead of using galvanized steel, mild steel wire, we would be using a large reinforcing rod, or rebar reinforcing bar like this. It's a fairly hefty one, and you can see it's ribbed on the side here, so that when the concrete sets around it, there's very little chance of this slipping in the concrete when it's under tension. And in this case, I think it's very interestingly, the end of this rebar, you can see that it's necked, and it's been under a lot of tension, and it's finally finally fractured in a ductile fracture, where you've got that cup here, and then there would have been a corresponding cone on the other bit of rebar when it failed. It's been put under a lot of stress. Okay, so reinforcement, steel reinforcing, creates a change in the original material of concrete, and a mixture of the properties are applied, and we can customize the properties of objects by using composite materials and joining them together with other materials. Now, a few different things that you need to know. One of them is that concrete can be, or concrete beams can be reinforced and created in a lot of different sorts of ways. They can be precast, which means that they can be, instead of assembled on site in a building, they can be made into a mould off-site, somewhere else other than the construction site, and then brought in on-site when required and fitted into position. That's called being precast. Especially useful if you want to create lots and lots of the same size shape, and you need them pretty quickly. Now, one of the issues with precast items, whether they're small items like a culvert for a drainage system, or whether it's larger items like large flat, you see those large flat walls that are assembled, and panels that are tilted up to create modern factory walls. The problem with them, creating them off-site, is transportation. On-site, they're large, they're heavy, and they can be a problem to transport. So that's always a limitation with off-site casting and moulding. So many of the larger items are actually cast on-site. Sections, things like column sections, wall slabs, bridge deck sections, a lot of these things, ducts, tubes, they're all made off-site and they're precast. Now, once they're precast, if they're just simply concrete, they still have the properties of concrete. They can be quite brittle. So to fix that up, we can put simple reinforcing in like this. Lay a mesh down and pour the concrete over the mesh, let it harden and solidify, and you get quite a strong structure. But in some cases, we don't want to have simply a strong structure. We need a fairly light structure. So if this was a beam supporting, say, a large span of a bridge, then we would want to reduce the size of the beam as much as possible, and at the same time be able to put it into place with a minimum of fuss. So we need to reduce the weight and the dimensions of the beam. So in that case, if we can create an additional force inside this beam that will need to be resisted before failure can occur, then we can reduce the actual size of the beam. So the way that's done is there's two main ways. The first one is to pre-stress the concrete. So when the concrete's being made, the beam's being cast in a mould, some tendons, these metal reinforcing rods, will be laid out and they will be put under tension. So there'll be some, like if you can imagine elastic bands, they do stretch, and they're stretched like this one over here, but not to failure like this. And when they're stretched, in their stretched state, the concrete is cast. When the concrete sets, it grips over here, then the tensile pressure on the beam is released, is taken off, and the beam then contracts and trying to go back to its original dimensions. Strain energy is abundant in there, and when it contracts, it places the concrete under compressive strength, and that compressive strength has to be overcome before failure can occur. So that's one way that pre-stressing, it's called, the concrete beams can be made stronger and lighter, and still perform the same sort of service properties as a larger beam. The other way is post-stressing, and post-stressing means that we're going to create a beam, and sometimes this is done in pre-stressing and post-stressing, but often if you have lots of large sections that you need to put together, for example a roadway of an aerial bridge, or a bridge that's suspended, or a car roadway that's suspended, a lot of the sections will be made in shapes that are precast off-site, and those shapes, I'll draw a picture for you, those shapes will be brought onto site and assembled, and they may look a little bit classic. Sort of a shape will be something like this. There'll be a hollow inside, so it'll all be hollow, and so there'll be a section like that, and there'll be holes inside that section. Those holes are cast in there, often with plastic tubes, and then afterwards, when all the other sections are lined up next to them, all joining together like that in a long line, then tendons or metal bars are run through these holes, and then a hydraulic machine will fix them at one end, crimp them at one end, and then tense them at the other end, pushing the whole group of modules together very strongly. And then once that they're under tension, concrete will be poured inside these holes to be able to keep the whole thing stable. Then there'll be a hydraulic machine will seal off the end, and then the remaining reinforcement bar will be cut off, And those 3 sections then have been post-tensioned, so they've been tensioned after they've been cast, as opposed to pre-tensioned when the objects have been, the tendons are pre-stressed and then the concrete is cast around the already stressed tendons. Here they're put in afterwards. And you can control, useful here because you can control the amount of pressure that you put afterwards. And what will happen here is these sections will also be glued together as well as post-stressed, and there'll be some locating pins and things like that to hold them all together. And that's often how a suspended roadway will be sitting on a column, and the suspended roadway will be set up like that. And you'll see these sorts of things, and you'll see the joints on them as you go. So that's post-stressing, and very useful when you need to reduce the weight of a member, and you can control very much the kind of stresses, compressive stresses that are placed under the assembly. Now, one of the advantages of post-stressing too is that it does help to close any fractures. So remember, concrete's a brittle material, so when it starts to crack like this, as it starts to crack, when the bottom, for loads coming when my fingers are pointing, starts to open up at the bottom, a crack opens up. Well, if there's pressure from my hands on either side, the crack closes up. And before that crack can open, that compressive tension has to, or compressive stress has to be released, has to be overcome. So you can see the advantage of post-stressing. Alright. Now, another means which can be used to create some, or shape a composite material other than pre-stressing and post-stressing with concrete are called slip forming. And slip forming, quite simply, is if you have a long object that you need to form, especially say a column, then the formwork will go around the column like that. The column will be rising up in here, and the formwork will go around the column. I should actually change it a little bit. The column will be shaped down in the bottom. So there's the column down here, I've just shaded it, and the formwork will slowly rise as the column sets. So this section up here, inside here, is setting. It's concrete that's setting, and there'll always be usually reinforcing in here as well. This is the formwork. So as the concrete sets, the form slowly rises up, allowing this bottom here will be partially set concrete, certainly at least stable, set stable concrete. And at the top here it'll be still wet and drying, so you get this form slowly moving upwards, and that's another way that it can be set. Now it's called continuous slip forming. Continuous slip forming. Now, I did mention to you that on large sites where you want to create some big walls, especially for factories, that they'll often form workers will create the slabs on site. So they'll lay out with some pegs on the ground, fairly straight ground, they'll make sure that it is straight, and they'll put in some formwork around like that, and then they'll pour in concrete in here and set a slab, and that slab will have some little holes attached where it needs to be bolted and gripped and moved, and it'll be shaped accordingly. And when it's set on site and the formwork is removed, and the concrete can be tilted upwards like this, and it creates a vertical wall section which will fit inside a slot. Usually you'll notice there'll be some mating slots down the bottom, and the concrete will just drop into that slot. Hydraulic rams will be used to hold it in position and steady it, and there'll be bolt holes that have been pre-cast into sections, so those rams can be just bolted in nicely, and same thing on the floor slab. And then when all the walls are fitted together, there'll be a steel framework, an internal steel framework that these slabs will be bolted to, and when that steel framework has been bolted together, the whole thing is stable. These don't have very much, can't take very much lateral stress. They can take plenty of compressive vertical stress, but not much lateral. So the steel framework is needed to be able to be mounted on, and basically they become panels that are mounted to a steel framework, which provides the structural rigidity. Now, firemen don't like trying to go in and saving these buildings, because steel will lose most of its strength at around 900 degrees Celsius. So you can imagine if this structure is relying on steel beams to hold it up, like a large factory, if there's a fire going on inside, the heat's contained within the building. It doesn't take long to reach that kind of temperature, and as it reaches that temperature, the steel progressively loses its strength, and then at 900 degrees it will start to becomes plastic and start to collapse. So these whole tilt panels start to then fold inwards or outwards, and they just become like a massive deadly cards that just fall over and flop down. So there are some issues surrounding the fire hazards with these large buildings made out of concrete tilt panels. But the big advantages are you can shape them any way that you want, place windows in any little direction. You can they're very convenient, they can be erected very quickly, and they're quite durable in terms of weather resistance. So there's a lot of advantages, and that's the reason why they're being used, and they're cost effective. So concrete tilt panels. Now, as well as concrete being a composite material, and by the way, just before we finish here, if we were to draw a microstructure of concrete, you'd have large aggregate sections like this in place, and they're irregular kind of shaped, although they can be sized roughly. And then you'd have lots of grains of sand, which I'm doing dots here to indicate. And the third phase that you see would be in between all that would be the Portland cement. The little dots are the sand, silica, and here you'd have your blue metal or basalt or whatever material is being used. Okay, that's what a microstructure of concrete would look like. You may be asked that question. So make sure you label all your diagrams when you answer questions. Always label every diagram that you draw, and try and use clear writing. I'm rushing this because I don't want to take too long. Okay. Now, let's talk about wood. Wood is another composite type of structure, and it comes in lots of different shapes and forms. Wood has many applications. It's easy to laminate it, to glue it together. So it can be laminated, and here's an example of some laminated wood. And you can see this would have been a part of a longer beam, and sections have been laminated together with a glue, usually a very strong brittle glue like urea formaldehyde would be used rather than PVA, polyvinyl acetate, which is water soluble and will eventually creep over time. It's more elastic. Urea formaldehyde is a thermosetting plastic and won't loosen up again with underwater or with changes in temperature. Okay, so this has been laminated for centuries. We spoke about the old bows and how they were used. And wood is made up of 60% cellulose, so 60% cellulose. It's made up of 28% lignin, which is a kind of glue, a natural glue, and 12% sugars. So that's its composition. It's easy to work, it's easy to join, it's got a very high strength to weight ratio, higher than steel, and has a relatively high stiffness. It's also a renewable resource, so we can plant trees and grow them again, but it will burn, so not fire resistant, and it's subject to fungal and insect attack. So one of the problems with wood is that it does have problems with its food for some creatures. So white ants love it. This has been a white ant section of wood. It's Douglas fir, Oregon, sometimes called, housing type timber, and you can see how it's been eaten away by white ants. Fungus can also rot it, and there are problems associated with wood in that sense that it degrades. Alright, now it's also, one other problem with wood is that it's anisotropic, meaning that it doesn't have the same strength properties in all directions or same material properties in all directions. So it also has imperfections like knots and grain in the grain, etc., which make it inconsistent in its strength properties, and if you get enough water on it, it actually swells, so it's dimensionally unstable with water. Now, it's stronger in compression that way than it is in tension, than twisting or by placing it in a bending moment, but because of its natural imperfections, its tensile strength of wood is reduced dramatically. It is very aesthetically pleasing though. So the options here for composites, wood itself is a composite structure, but creating building materials out of composites, wood composites are laminated beams, like these ones here, and you can also form plywood, and plywood's very useful here because it solves some of the anisotropic properties of wood by putting plywood sheets with the grain direction in opposite sensors. So the grain direction moves one on top of the other at 9 degrees. That means that it starts to have very consistent properties in compression and in tension. That's one of the reasons why plywood is very useful. Again, it has to be glued together, and you can see the striations indicate the grain direction. The darker ones being end grain, the lighter ones being along the grain of the different plies that have been put together. Okay, it's also used for formwork for concrete because of the strength properties, because of its lightness and easy of workability, and its renewable nature. It's used for bracing in houses, it's used for panelling, plywood is. So very useful. Now another material that's not quite as popular these days is called particle board. And particle board, you can see, is made up of lots of fine little wood chips, and they are being glued together. They've been glued together. However, as you can see that's happened here with this particular item, it's great because it has consistent dimensions, so it doesn't suffer from the wood grain issue that you have when you've got unstable strength properties because of the difference in grain pattern and knots, etc. So it's consistent. However, it's very much swells with moisture, and the glue inside it when it's being worked can create a fine dust as you're cutting and sawing it, and that's now seen to have some health problems associated with it, with particle board. Still used because of its cheapness and because it can be made in any sizes that you want, and that's another issue with natural occurring wood. Only occurs in certain sizes. And laminated or fibered wood can be made any size that you choose. That's a very handy thing. Alright, particle board has another little brother and sister which I don't have an example of, called MDF, or medium density fibre board, and that's a much finer item, more dense, stronger, and a bit more water resistant than particle board. Chipboard, as this is sometimes called. So that's MDF fibre board. Again, problems with breathing the dust in when it's being cut up. It can be quite unpleasant for you. Alright, next item that we're going to look at is asphalt. And asphalts can be naturally occurring. They're a kind of petroleum-based or oil-based product, so they can be naturally occurring. I've got some samples of some asphalt over here. This is pulled from the playground at Girraween High School. Now, these, although it seems quite hard, almost like a rock, it is a combination of different things. It's a semi-solid item. Although it seems quite hard now, if I start to heat it up, even hot sunlight, this will start to become more plastic. The matrix, which is essentially an oil-based product, starts to flow, and you'll be able to move it and shape it. And you can see that on a very hot day. You'll be able to see deformations in when there's been pressure put on roadways which are made with asphalt. Now, it's been used as a waterproofing agent for thousands of years. In fact, again, if you look in the Bible, you'll see the story of Noah and his ark. He used what the Bible called pitch, and pitch was simply a naturally occurring asphalt which was abundant in those areas at the time, to waterproof the boat. So it has waterproofing qualities, and it has adhesive qualities. It sticks a lot. In the old days, you remember some people would be tarred and feathered as a punishment for their crimes, and especially in the Wild West. Well, putting a hot tar on them would be unpleasant enough to say the least, but putting feathers on them on top of that, tarred and feathered was one of the ways that the adhesive nature was used of asphalt. It can be coated onto metals such as aluminium, and it resists chemical and water action. So you'll be able to buy damp course now, which is basically a protective moldable kind of sheet which is used to shape around, especially roofs, where you want to be able to have tiles that leave gaps and you want to be able to shape an object around. Aluminium coated in asphalt now replaces what used to be lead flashing. So the asphalt qualities of water resistance and flexibility are being used there. Now, it can be mixed with aggregate, gravels and sand, and form road base, or road surface, not road base, but a road surface, such as what I have here in my hand. Another use is impregnating. This is a fibre that's been impregnated with asphalt, and it's used as an expansion joint between concrete slabs. So when it stops the slabs from cracking, then you provide a weak area, a weakness where it allows a bit of movement, and this is an expansion joint, and it's been impregnated with tar or asphalt to be able to make it useful. You want it to be able to last and not break away, So its waterproofing qualities and flexibility is important because you've got to shape it into corners and fit it in. So that's another use of asphalt as a jointing in between concrete slabs. Alright, so much for asphalt. Now with asphalt, important to notice that the aggregate that's mixed in here, just like concrete, if it's used on a road base, which is often the case, probably its biggest used, the asphalt is flexible, so it doesn't crack like concrete. It will bind together and hold harder elements like stones, etc., that will provide wear resistance, which is essential for a road. And it can easily be replaced. It can be heated up and rejoined, which is another great advantage to it. And it can be made up in large or small quantities. So it can be applied at fairly low temperatures. It flows at quite low temperatures. So it's not necessary to be able to heat it up. It's quite convenient as a road system. And of course that's why you see so much of it. Alright, so that's asphalt. Now lastly, before we move on, I just wanted to show you this. This is fiberglassing, or basically an application of fiberglass. It's a composite material, so it's a grinding wheel, a masonry cutting disc from a grinder, a 9-inch grinding wheel. It's worn down a little bit now, but you might be able to see and notice that fabric kind of cross pattern that you can see here. It's more obvious if I turn it over. You see the cross pattern? Well, that would be fiberglass, a fiberglass sheet that's been put into an epoxy probably as a resin, and mixed into the epoxy has been silicon carbide, very hard, very tough, very brittle material to provide the abrasive hardness that's required. But these discs are incredibly flexible and stiff and durable, so the combination of the epoxy resin and the fiberglass reinforcing means that the flexibility and the tensile strength of the fiberglass is transmitted to the overall disc and through the resin, and the disc becomes, even spinning at 3000 RPM, it's not about to shatter and kill the person using the disc. So a great example of the way that combining materials using a matrix and a reinforcement can produce the best of both worlds for material usage, and that's probably why they are the building materials of the future now. Alright, one last thing. We're going to talk about geotextiles. Geotextiles, the word geos, again, Greek, the earth. Geotextiles. Now textile is a woven fabric, and geotextiles, I don't have some examples to give you here unfortunately, so I thought I'd grab some on the computer for you and show you some of those. And I'll take this off, so it might be a little bit jerky, but we'll do the best that we can. Okay, so there's an example of a geotextile, 3 different sorts. Their main purpose is to provide drainage, reinforcement and filtration, and the separation of soils in construction and civil engineering applications. So if I were to wind this down a little bit further, you can start to see, here we go. Yeah, so you can see down here some applications of geotextiles. There's truck dumping some stuff on the ground. Underneath pavers, a sand base, pavers on the top, sand, and underneath the sand the geotextile. Even on large areas, the geotextiles, they can be woven mats like this, looks a bit like fiberglass being woven, or they can be something that's far more consistent, and they really have a huge impact on soil erosion, and that's probably the most popular usage. I'll try and find you an example over here. Yeah, so if we could look over here, you can see this big hill over here was needing to be stabilised. With water action, they'll be running. Large amounts of water will drag soil and there'll be erosion. Place a geotextile on top and you can cause moisture to flow through the geotextile. At the same time, because if you put dirt on top of it to keep the geotextile in place, it'll form almost like a lamination that stops movement and slippage of the subgrade underneath the geotextile. So it's very, very useful, very powerful in that kind of setting. Here's another example, pretty good example. This is just straight off Google Images here. You've got an aggregate placed around a pipe, obviously because water needs to be collected or run off from that pipe and be distributed. That looks like an agricultural pipe, so it'll have holes in it. So water will flow through and needs to be distributed. If this aggregate is left as it is, the soil will start to seep into it over time, and its usefulness as a drainage system will be eroded, as soil starts to clog all those areas. And so keeping the geotextile around, it holds the whole thing together, lets the moisture come through, stops the soil from penetrating into the aggregate. Alright, find you one more application, I think, of geotextiles. Yeah, so this is probably a good one over here. Okay, so you can see over here looking at this, that there's a car tyre on the surface of a road. Without a geotextile, over time, the road aggregate layer underneath the road surface starts to break down and mix in with the subgrade, the native material it's called here. With a geotextile, the various different layers are kept together, and the strength properties of this whole structure remain consistent, which is what you want, what the designers want. So that's an important use of geotextiles. And you can see, I guess I'll show you over here how some of them have been structured. So you can see that there's some mesh with some absorption material on either side, and that can be created in lots of different ways. So that's essentially the use of geotextiles, and I hope that that whole thing was useful for you. The idea of geotextiles is that they're made from polypropylene or PVC, usually polymers, or high density polyethylene, sometimes even polyester. And the idea is that they have high tensile strength, they're tough, and they resist corrosion. You can buy or get some geotextiles that will biodegrade, if that's what you want, and most of the time they're laid onto a soil surface, over which there's going to be a road or some other system put on top. And very frequently that's necessary when you've got a bridge that's passing through somewhere, and the bridge is suspended like this, and on the lead up to the bridge you've got a hill, and the hill is made of some sort of dirt that's been built up there to allow the road system to travel through. But this here, if it begins to erode, will destabilise the whole bridge, so geotextiles are laid over this area to be able to keep it stable and structurally sound over time. So a very useful material.